I'm Shayan. I'm a machine learning specialist solutions architect based out of Berlin in Germany. And in this section, we will talk about data preprocessing bottlenecks caused in computer vision workloads and how can we address them. So we will start with defining what the problem exactly is with CPU bottlenecks caused due to data preprocessing and why is it so challenging, and discuss a customer use case. Then we will discuss some best practices to resolve it, and then we will move on to an experiment that we've conducted earlier to see how we can address the CPU bottlenecks by offloading data preprocessing to GPU. And we will look into Amazon SageMaker debugger on how we can leverage the tool to identify to identify bottlenecks and system utilization metrics. And then finally, we will zoom into one particular training job and look into some metrics and how we are able to improve training time. So yeah, before we get started, the high-level overall picture of what typically happens during a training job when we are using Amazon SageMaker or in general for computer vision is we have the data on some storage, and we need to move the CPUs on the SageMaker training instances requires to fetch this input training data batch by batch. And this is the part which Gilly spoke in the earlier section about the different file modes that's available and the different pros and cons of the different IO modes that's out there. And once CPU has this data, typically image decoding and pre-processing operations are performed on it before passing on to the GPU for the training loop. And once this pre-processed data is on GPU, the forward and the backward passes are run for the training cycle, and GPU periodically passes back model weights, loss, matrices, etc. to the CPU. And then finally the CPU does if there is requirement for some post-processing on the data. Otherwise, just passes back periodically statistics and generated checkpoints back to the storage. So typically, especially steps 1, 2, and 3, this is what the cycle happens for every input batch of training data. And what we focus in this session is the bottleneck that is caused in the step 2, where the GPUs actually keep waiting for the data while the CPUs are still processing them. So based on different computer vision use cases, be it pose estimation or object detection or segmentation, we often require heavy image augmentation operations that needs to be done on the input data. And GPUs are the more expensive resources. So GPUs can perform terafloating point operations per second. So they can do the operations much faster than CPUs, but they can do this only if the data is available in the GPU memory in a timely fashion. And that is often not the case when a bottleneck occurs. So in data pre-processing, there are basically two major steps: decoding and augmentation. And decoding of JPEG images can become quite CPU intensive or compute intensive in general. So, and it also depends a lot on what kind of model you are using. If your model is more CPU intensive or GPU intensive, that also makes sure that where the load would be shifting. So in a nutshell, we can say that if we consider the ratio between the amount of data that needs to be, or the load of the pre-processing that needs to be done on a given amount of data, and the model computation, the amount of computation that needs to be done from the model side on the GPU, when this ratio becomes greater than the CPU GPU ratio for your SageMaker training instance, that's when the bottleneck occurs and GPUs begin to wait for the data to arrive before it can process it. So what is the challenge in this particular problem? Why is there not one single silver bullet with which it can be resolved? So as we know, Amazon SageMaker offers an array of instances with different CPU and GPU ratios. So for example, if we talk about single GPU instances, P32X large has 8 CPUs, whereas G4DN 16X large has 64 CPUs for a given GPU. But the challenge lies in the fact that for a given use case, depending on how much augmentation we need to do and depending on what kind of model we are using, this requirement of ratio constantly keeps changing. And it becomes difficult to address this problem by simply upgrading your instance. So we have quite a few computer vision workloads from our customer on Amazon SageMaker training jobs, and one of them being document verification. This is a use case where the customer has very large amount of growing data with average JPEG sizes of 2 MB, and they face the similar challenge that when they use smaller models, this causes GPU underutilization because there's a bottleneck caused in the CPU. And when they move on to more larger models, they tend to hit the GPU bottlenecks. So, how do we address this challenge, and what are the different ways we can fine tune to improve our system utilization? So, the very first thing that we can start with is to identify the best suited instance to start with. It might not be the most ideal one, but at least the best one that we can choose of the array of options that we have. So this would basically depend on what kind of load of augmentation do you have. Do you have very heavy augmentations or lower augmentation, and the size of your batch size and your data set? And then on the other hand, the model complexity, if you are using a lightweight model or a heavyweight model. And depending on these factors, you could experiment and choose what is the optimal ratio between the number of CPUs and GPUs that you can have, so that GPUs wait the least amount of time for your CPUs. And next comes the more tricky part, where you identify an instance to start with, but what else can you do other than upgrading your instance, which might increase your cost but not improve your performance accordingly, thus reducing your performance cost ratio. So once you have your instance, it's important to load balance among all the CPUs in your multi-core CPU system. So one good practice is to choose the number of workers, one less than the number of CPUs that you have. This works good for smaller instances, but as you start using larger instances with much larger number of CPUs, having increasing the number of workers might not scale your performance accordingly, and this is because you might hit the potential concurrency bottleneck of your file system. Depending on which file system you are using, you might have an upper limit on how many workers you can use to concurrently access the data without causing bottleneck. So depending on what file system you have and what is the upper limit, it's important to choose the number of workers that you can have to parallelize the workload among all the CPUs as much as possible. Then there are different other CPU optimization approaches that you can take on a lower level. For example, it's a good practice to use lower precision as much as possible and postpone casting to higher precisions to the end of the pipeline. Similarly, also, depending on what framework you are using, you can have specific framework binaries that you could compile and configure to leverage available CPU extensions, such as, for example, the advanced vector instructions. So, and also it's important to note that with the batch size, if you increase the batch size beyond a certain limit, it might be causing you CPU bottlenecks. But also reducing the batch size doesn't necessarily always solve the problem, because you might be affecting your model convergence or causing underfitting, or at the end of the day, with the lower batch size, you might be increasing your training time by a lot more. So there needs to be some experiment done based on the different parameters you have to optimize and maximize your CPU utilizations for not just for one CPU, but for all the CPUs in parallel, how you can maximize them so that the GPUs are not waiting for the data. Apart from this, when it comes to augmentation, typically we do the decoding and augmentation on CPU. But one approach is, what if we can move some of the heavy pre-processing step to the data preparation phase? So for example, operations that do not depend on any hyperparameter, or they are not applied randomly. So if we move those to the data preparation phase, then we might be reducing the bottleneck to a large extent. In that case, we also need to take into account that how much do we want to prepone, because this can end up increasing your training data size massively and thus start creating IO or network bottleneck. So that needs to be taken care of, that while resolving one bottleneck, you don't end up creating another bottleneck. There is also the option of offloading your data pre-processing to other machines. So that means if you have a separate CPU instance where you can pre-process your data and then not cause bottleneck in your GPU instance, the CPUs in your GPU instance, and then maximize the system utilization. Here also one important thing to note is if we have dedicated separate workers for doing the data pre-processing, the instance needs to have good enough network bandwidth so that the overall performance is not affected by the large amount of data transfer that might be involved. And Amazon SageMaker has heterogeneous clusters in the roadmap to address this challenge by introducing heterogeneous clusters where you can have dedicated CPU workers to do your pre-processing in a separate instance while you do not let your more expensive resources like GPU instances stay idle. This is on the roadmap. Feel free to reach out to the SageMaker team if you want more information on that. Next comes the approach of moving some of your data pre-processing to the available GPUs. So as we mentioned earlier, decoding on CPU is quite compute intensive. And if we can move these decoding and augmentations on GPUs and load balance the CPUs and the GPUs available, then that can address your bottleneck and improve your training time. In this case, it needs to be taken care of that if you're moving augmentation to GPUs, that means essentially you're increasing the computation graph on GPU and thus increasing the GPU step size. So in that case, you might need to use lower batch sizes to free up the memory and the GPU for this augmentation and decoding to take place. So that's something to take care of. This is the approach we will deep dive a bit more with by showing the results of an experiment that we conducted earlier. So for this experiment, the goal is to reduce training time by addressing CPU bottleneck caused by data preprocessing. And we would do this for models of different complexities and see how that is affected. And we achieve this by moving JPEG image decoding and augmentation load on the available GPU in the SageMaker training instance, thus load balancing the CPU and GPU better to improve the system utilization overall. And when it comes to what throughput are we looking at, in this case, SageMaker training at the end of the day is meant to take care of your undifferentiated heavy lifting. And SageMaker in the background spins up ephemeral clusters for just the number of training seconds that you have, and you pay only for that amount of time. So we take seconds per epoch in this case as a metric, because if we can reduce the seconds per epoch given all the other parameters are the same, then not only we improve the performance, but we are also reducing the cost for the expensive instances that we might be using for training. And we also look into system utilization overall to see where are the bottlenecks and how we can address them. For this experiment, we use a subset of the ImageNet dataset of around 1 GB with an average image size of 144 KB. And we go through different models of different architectures of different complexities, from ResNet 18 to ResNet 50 to a more GPU intense model, ResNet 152. We do this experiment on a comparatively smaller instance of P32X large with 8 CPUs and 1 GPUs. Because the goal is to be able to create a bottleneck and then introduce a new approach with which we can address this bottleneck. And then as the data set or the model or the augmentation load might increase, we can scale up vertically and then scale out horizontally as and when required. And we use PyTorch for this SageMaker training job with bring your own script training approach. And we use a batch size of 32 in this case and run it for a couple of epochs with 300 steps in each epoch to measure the seconds per epoch. So yeah, what are the augmentation operations that we essentially do? So the first step is decoding, as we mentioned. In this case, we have JPEG images, so there needs to be decoding done on them before any pre-processing operation can be applied. And then the next step is the augmentation operation itself. So in real world, there could be several heavy augmentation operations such as Gaussian blur or dilation or jitter or augmentations like that. For this experiment, what we do is we take horizontal flip, vertical flip, and random rotation and increase these augmentation by a given load factor to compare benchmark results to mimic the real world scenario where we might have a lot of heavy augmentations. And once we have this augmentation, we basically resize the image, normalize it, and then crop it. So these augmentation approaches for our SageMaker training job, what are the approaches that we are using? So the first approach, the baseline approach that we use is using the PyTorch data loader to decode and augment JPEGs on CPU. So this is the baseline approach that we use. And then the other approach that we introduced is using NVIDIA DALI, the data loading library from NVIDIA, to move decoding and augmentation on GPU. So NVIDIA DALI is a library, is a framework that's highly optimized to run data pre-processing operations and move part of your data pre-processing pipeline onto the GPU, and is highly optimized for NVIDIA specific GPUs, which is the case in this experiment with P32X large. And it also comes with the built-in library of NVJPEG, which helps with GPU accelerated decoding, which is expected to be much quicker and faster than decoding JPEGs on CPU. So having said that, let's look at how the results look like when we run some experiments with this setup. So on the x-axis, you can see we have the augmentation load factor increasing from 1x to 12x, increasing the load of the data pre-processing operations. And on the y-axis, we have the seconds per training epoch. And basically, we have two approaches, PyTorch on CPU and DALI on GPU, the two approaches that we just discussed. And we perform these two approaches on 3 different models. So we have essentially 6 different combinations. So this is how it looks like when we run training job for the ResNet 18 model with PyTorch on CPU. And when we rerun the experiment with moving the augmentation to the GPU, the decoding and augmentation with NVIDIA DALI, we see that the training time, seconds per epoch, reduces drastically. And it's also important to note that as we increase the load, in this case with DALI, the seconds per epoch doesn't increase as much as it was increasing for the PyTorch on CPU approach. So that really shows that you have a bottleneck out there which is being addressed, and as long as the bottleneck is being addressed, you can keep increasing the load till the bottleneck is hit again, and then you need to take different other approaches. So this was for ResNet 18, the more lighter model. We repeated the experiment for heavier model of ResNet 50, where the overall training time increased and still the bottleneck was still addressed. And then we repeated the experiment with ResNet 50 by first doing it on CPU, and then repeating the experiment with augmentation, decoding and augmentation on GPU. So in this case also we see there is quite a bit of improvement. So in general, how does the improvement look like if we compare every model while we increase the load factor? Before going into that, this particular chart that's been marked in the orange, this is an experiment we will dive deep in a bit later on ResNet 18. But first, let's look at the different models. How much did we manage to gain or improve? So this is a chart where on the y-axis we have the improvement in percentage, and on the x-axis we are increasing the load factor. So you can see for the 3 models the lighter model ResNet 18 has the maximum gain or maximum improvement in training time when we address this bottleneck. I mean, theoretically, if you think about it, this is expected because lighter models like ResNet 18 tend to cause more CPU bottleneck than heavier models, more GPU intensive models like ResNet 152. So, depending on what is your scenario, how much data you have, how much augmentation load you have, and what kind of model you have, the impact you can create by moving your decoding and augmentation on GPU can vary a lot. And that is evident in this particular comparison. Now we will dive into one particular training job. But before that, let me talk a little bit about Amazon SageMaker Debugger, which is a feature that comes with Amazon SageMaker training. And this is a toolkit that helps you monitor your system utilizations. So you get to see real-time visibility into your model training. You can either do it using your Python SDK, or if you are using SageMaker Studio, you can look into it interactively. Debugger also gives you a profiler report where it gives you a certain list of recommendations on resource optimizations. So this is something we will see later on when we move to SageMaker Studio. How based on certain pre-built rules, number of times they are being triggered, you can get recommendation on if you should increase, if it's the issue with your CPU bottleneck, or if it's the issue with your batch size or GPU memory, or whatever the other reason might be. And apart from that, you can always monitor and report system resource bottlenecks, which of an example of which we will see very soon in the next slides. So, talking about the different experiments that were conducted, we dive deep into this particular experiment that's shown with the ResNet 18 model on MLP3 2x large instance for a batch size of 32 and a heavy augmentation load of 12x on the flipping and the rotation. So we run the training job with these parameters by running the decoding and augmentation on CPU. And we see the seconds per epoch to be 77.82 seconds. So this is a screenshot from the SageMaker Debugger Profiler report that we spoke about earlier. Here it is a subset of the whole report. And here I focus on the CPU and GPU utilization, the max, min, and the different quantiles in which the utilization percentage that is visible. So for example, in this case, if you look at P95, we can conclude more or less that 31% of the time, 95% of the time that the GPU was utilized 31%, and 95% of the time CPU was utilized 100%. So that clearly shows a bottleneck that is being caused and GPU is being underutilized. This is a chart I plotted using the SageMaker Debugger SMDebug library. And on this chart, you can see the first 8 rows are the CPU utilization and the last one is the GPU utilization. And here yellow indicates 100% utilization and purple indicates 0% underutilized. So it's evident here when I zoom into the bottleneck portion, it's evident here that there's quite a bit of bottleneck caused in the CPU. And this is causing the GPU to constantly stall, having like cycles where it is stalling and dropping to 0% and again increasing and again dropping to 0%. So this is something which is an undesirable state given that GPU is an expensive resource and you do not want to underutilize it for your performance cost ratio. So we run the same job, training job with moving the augmentations on GPU with NVIDIA DALI, and we managed to reduce the seconds per epoch to 21.33. So that's an improvement of as large as 72%. If we look at the same profiler report, we see that 95% of the time the GPU has now improved its utilization to 55% and CPU has come down to 64 from 100%. So that really shows that there is still some more potential to increase the load or increase the batch size to maximize the utilization. But we kind of managed to balance the load between CPU and GPU and improve the GPU utilization, which was our aim. And in the same plot, you can also see the utilization heat map, that we managed to improve the GPU utilization. And also there are less bottlenecks once the epoch starts on the second half of the graph, uh, thus causing the GPU to be better utilized. And not once that we do the GPU accelerated decoding and augmentations on the GPU. So yeah, that's more or less what I wanted to show about the experiment in general. Yeah, so here's the repository that has the implementation of using NVIDIA DALI to do your decoding and augmentation on GPU when using SageMaker training with bring your own script approach. Uh, the repository is at the moment on AWS GitLab internally, and you could play around with the different parameters out there with the batch size, for example, or the different model complexities or the load of the augmentation, and try out for your use case how could you toggle these parameters to reduce the training time by moving your augmentation to GPU by addressing the bottlenecks. On the right, I also have some useful resources related to best practices for overcoming data preprocessing, optimizing your GPU performances by addressing bottlenecks, and also using SageMaker debugger to identify bottlenecks. That's the third blog, what it's about. And also there's a deep dive blog on if you want to customize further using NVIDIA DALI, if you want to customize only a part of your pipeline to better load balance and address your bottleneck. So that's a nice blog on deep dive with NVIDIA DALI as well. And with that, I would like to move to SageMaker Studio, where I have this repository that I just showed cloned, and this is a notebook from the repository. And as you can see, I run a training job here with a ResNet 18 model for a batch size of 64 and a load factor of 12 on P3 2x large instance type for both PyTorch CPU and DALI GPU. And once I run that, you could see here I have the seconds per epoch, which is 58.29 in this case. And I also have this chart from using the SMDebug library that we discussed, where it plots an interactive chart to show the bottlenecks and how the GPU is starving and not being fully utilized. So there's the util debugger script there that has been used to plot this chart, and there's the util train script for the SageMaker training estimator. Yeah, and this is also another chart that's been plotted using the same library. This is basically a histogram of the utilization of the 8 CPUs and the 2 GPUs. And you can see this is an example of a bottleneck. So there's quite a bit of spikes on the right hand side, almost 98-100% for all the CPUs occurring very frequently, and the GPU is underutilized. Yeah, so these are some examples of insights that you can gain with your Python SDK leveraging the library. If you move into this section of Amazon SageMaker Studio and go into experiment and trial, you can look for your training job ID here. And once you would find your training job ID, you can open debugger for insights for a more interactive version of checking reports and bottlenecks. So I have this one opened for a particular training job. And as you can see, this is the report that we showed earlier in the slides. This is extended by GPU, CPU, IO, and network. And the report also has a pie chart showing that the green part is basically low GPU usage due to CPU bottlenecks. So this kind of summarizes the issues that you might be having with your current training job. And if you remember, we spoke about the recommendations. So here it also provides these recommendations that there has been issue found with GPU memory increase, low GPU utilization, CPU bottleneck, and batch size. So based on some predefined rule, how many times they are getting triggered, these recommendations come along. and you can check the details for further deep dive to understand if this is something you would like to address for your training job. This is the overview section. You can also download the PDF report directly from here or access it on your S3 bucket. And if you go into the notes section, there's also some more charts on CPU utilization over time, network utilization, GPU utilization, and also a similar heat map. So yeah, that gives you an overview of both interactively looking at the insights and also using the library. That's more or less what I wanted to discuss in this session. Hope it helped. For any questions, please feel free to reach out. And yeah, thanks a lot for hearing.